All right, we're on to a couple more examples of how to solve systems of linear equations with the elimination method. Now, again, what we're doing is we're transitioning away from substitution method on certain examples, those examples which aren't already solved for a variable or aren't necessarily easy to solve for a variable. Now, your ability to be successful on this video actually has to do with common denominator. Do you remember adding, subtracting fractions? In order to add or subtract fractions, you need a common denominator, same bottom number. How you get that, when you find the LCD or lowest common denominator, it's actually the least common multiple that you are finding. You're finding the smallest number that both of your denominators divide. We're actually going to use that here. You see, with the elimination method, if we didn't want to use the substitution method, now this one might not be so bad. Subtract 4x and you could do substitution method. Watch that video if that doesn't make sense to you right now. If you don't know that you could subtract 4x and do substitution method, you're not far enough along. Go back and watch a substitution method video and then come back to this. But let's say we don't want substitution. Let's say that's one more step that we don't have to take. You're right, and we can do elimination method with this. But in order to do that, well, let's check this out. One of the first steps was, let's make sure that all of our variables are on one side. Well, they are. I've got x's, I've got y's, I get number. I get x's, I get y's, I get number. And we have this lined up vertically. So we have x's on top of x's, we have y's on top of y's, but there's something missing. What's missing is that I need my variables to be opposite terms. I need them to be exactly the same look with a different sign in front. Those aren't the same, and they don't have a different sign. The y's have a different sign, but they're not exactly the same. So here's where the whole, what I was just talking about, the LCM, the least common multiple, here's where it comes in. What we're going to do is we're going to try to find a way to force these terms to be the same. And it's going to be through multiplication. Here's what we're going to do. Basically, we're going to look at our two terms, our x's, and we're going to look at our two terms from our y's, and we're going to figure out which one is going to be the easiest to find the LCM for. Basically, that's the smallest one. So we're going to find out which two terms are easiest to pair up. So imagine this for a second. Imagine you had 3 and 4 on denominators, and I said find the common denominator. And you'd think about it for a little bit, and you'd go 12. Because 12 would be the smallest number that both of those coefficients divide. That would be 12. 4 doesn't work, 8 doesn't work, 12 does work. Now, try to find it for these two numbers, 2 and 1. Well, the LCM there, if you were thinking of denominators, same idea. If you're thinking about that, the LCM there would be 2. 2 divides 2, 1 divides 2. That right there is called the least common multiple. It's the smallest number that two or more terms divide into. That right there is going to determine what pair of variables we're going to make identical or opposite terms. So identical terms, opposite signs. Whatever your smallest LCM is, that's typically what we use. Whatever one's easy, some teachers say whatever one's easiest, whatever's easiest to make the same. Whatever takes less multiplication, that's a great way to look at it also. All those things are fine, but what we're all trying to tell you as teachers is, or whoever's teaching you, if you do it on your own, is don't make this harder than it has to. Pick the pair of terms that's going to be the easiest to match up, the easiest to make opposite terms. 3 and 4 is not it, because you'd have to multiply 3x times 4 and 4x times 3 in order to match up 12x. And you'd have to multiply one of them by a negative because you need your signs to be opposite. 2 and 1, that's a lot easier to make into the opposite terms here. They already have different signs, and on top of that, my LCM is much smaller. So we're looking at this, let me recap the whole thing for you. We're looking at this. Variables on one side, numbers on the other, it looks great. X's over X's, Y's over Y's. This does not look good, and this does not look good. What's easier to make into opposite terms are the Y's, for two reasons. Number one, we're getting a smaller LCM. Number two, I only need to multiply this y by something, and I can make it an opposite term to this. The 3 and the 4, I have to multiply both of those terms. Pick the easier work when possible. So here's how we do it. We look at this and go, well, I'm going to try to match these variables up. I need to multiply this by 2 in order to get the same exact term with opposite signs, opposite terms. The only problem is you can't just pick and choose what you multiply. If you're going to multiply one term by a number, wait a minute, the only way to get in there is to multiply this whole side by 2. But if you're going to multiply one side by 2, you multiply the other side by 2 to keep an equation actually equal to what it originally was. What that means is, if you're going to multiply one term by 2, you multiply everything in that equation by 2. Most people show that just by doing something like that. Whether that's mathematically appropriate or not, I'm not too sure. Mostly we'd have times 2 times 2. That's typically what we would normally do in an equation. But here we kind of use this loosely, understanding that, well, you're multiplying every single term in there by 2. Kind of a distribution property on an entire equation, if you will. So, on our first equation out of the system, nothing changed because nothing needed to change. We're really just focused here. We just have to multiply the entire equation by 2 to keep everything equal. What that means we'll get is 8x plus 2y, and then we'll get 14. Notice what it did. Notice what it did. They kept everything in order. It still has x's, y's, numbers, but now I do have one variable that pairs up as opposite terms. That's exactly what we're looking for. So the first one didn't cut it. I didn't want to use 3 and 4 because that's 2 multiplications. I'd have to multiply this whole statement, this whole equation by 4, and this whole one by 3. Would it work? Yes. Is it too much work? Absolutely. Pick the easier way to go here, and that would have been our y's. So now that we got this, man, that's fantastic. We're back to the last video where if we have our variables lined up and we have one pair of opposite terms, let's just add the entire system. If we do, we get 11x. We get 0 y's. The y's are gone. We've eliminated them. Make sure to be in opposite terms and adding. And here we get 22. If we divide, so now we're back in the last video here. We've already hopefully learned this and practiced it. X is 2. Remember what we're doing. We're finding out where these lines cross. We know that the first half of that point of intersection, that x-coordinate is 2. Now we're going to use one of our original equations. Don't use these ones that you've manipulated. Not necessarily that it's wrong, but usually to get here you have to multiply. Well, your numbers are bigger, so deal with something a little bit simpler. I deal with one of these two, one of the originals. I'd actually probably deal with that guy right there. The 4x plus y equals 7 looks a little simpler. So I'm going to rewrite that. Some people do always ask me though, well, is it wrong to use that one? Not at all. Is it wrong to use these two? No, it's not wrong. It's just that the numbers get larger, just a little more complicated to deal with. So usually sticking with the original equations is the best practice when dealing with elimination method. So I've rewritten this. I know that my x value is 2, so we're going to plug that in. Let's see, that's 8. If I subtract 8 on both sides, we get -1. Now, one thing I do want to tell you, when you're plugging in this point, this is a big deal. A lot of people miss it, okay? So don't miss this. When you're checking this point, don't check it here and here. And the reason why you don't check it here and here is if you happen to make a mistake from this first step to here, it will not show up. So we want to always check the point of intersection on the original system before we've done any work at all, because that's where it really matters. Suppose you make a mistake from here to here and it works here. You go, yay, I'm done. Yeah, but you're going to fail that problem because it might work here, but if you've made a mistake, it's not going to work in the original. So we check this in the original system. So let's do that just for our peace of mind to make sure that we're moving on with a knowledge of having the correct point of intersection. So x is 2, y is -1. That would give us 6 minus -2, which is 8. So I know that that point is on that line. We'll plug that in here as well. 8 minus 1, that's 7. So I know for sure that that is the point of intersection of my original system of equations. That's what we're talking about. So yeah, it takes some multiplication to get these things to to match up, to be opposite terms. I want you to look at this next one. Let's see how much of it you could do. Okay, try it on your own if you want to. Ask yourself the following questions. Firstly, is it set up better for substitution, or is it set up better for elimination? Sometimes it's not perfect for either one, but which one would be easier here? Well, substitution would have to be solved for one variable or easy to solve for one variable. I don't consider either of these to be easy for one variable. This one was. One-steppers, that's pretty easy. But when I'm starting to deal with two steps and dividing by negatives, that's not a good thing for solving for a variable here. So that's a no. Are my variables lined up? Do I have x's on top of x's, y's on top of y's, numbers on top of numbers? If the answer is yes, then the most important part is, do you have one pair of variables that is opposite terms? If the answer is yes, you just add the system. You're almost done. If the answer is no, I want you to think right now, what is easier to make opposite terms, x's or y's? And once you've thought of that, which one's easier, the x's or the y's? It has to do with the smaller LCM. And then see if you can multiply. I'm going to do that in a couple seconds, but I want to give you an opportunity to check that out. Well, I'd look at it, man, to make these the same number, to make these opposite terms, so same number, different signs, I'd have to get the LCM of 10. You see the 10? It's like a common denominator. But I need to multiply this by 2 and this by 5. That means the entire equation by 2 and the entire equation by 5. And one of them would have to be negative. So negative 2, positive 5, or positive 2, negative 5. Doesn't matter which. Would it work? Yes. Is it the best way? No. Because this LCM is 3. And it already has different signs, opposite signs. The smaller LCM typically drives what variable you're trying to match up there. So a lot of people ask, how do I know? How do I know which one? Number one, it doesn't matter. But number two, pick the easier one. So pick the one that's giving you the smaller LCM. This is like the common denominator, smaller of the two, would be generally the most easy to do. The x's aren't it here. If you saw the y's and you're like, yeah, that's how it has the opposite sign already, all I have to do is multiply, let's see, if my LCM is 3, that's already 3. All I would need to multiply is this by 3. If you saw that, that is awesome. That's exactly where I want you to be. So x's, no, that's too much work. As far as making the y's the same, that's pretty easy because all we have to do is multiply this top equation by 3. This one doesn't need it. I already have the 3. That's the smallest number that both of those coefficients would divide. I don't need to multiply by a negative because I want my opposite signs in there. That's a lot to take in. Let's make sure that we get this. X's, no go. We'd have to multiply both by a different number. One of them would have a different sign. That's too much work when we have a better choice for y's. 3 is the number that we can make both of these terms into. That's great. And they already have opposite signs, which is what we want when adding systems together. So let's multiply the entire top equation by 3. So 15x minus 3y minus 33 looks pretty good. This bottom equation doesn't need to change. That's why we chose those y's, so that we didn't have to multiply more equations than we need to, or by larger numbers than we need to. That looks pretty good. X's are still on top of x's. Y's are on top of y's. Numbers on numbers are lined up vertically. We're going to take a look at that and make sure that we have one pair of variables that are opposite terms. We certainly do. That's why we multiplied by 3 to make that. Of course, both our variables aren't going to match up and be opposite. Otherwise, we'd eliminate both of them and we'd end with either no solution or infinite solutions. We'll talk about that in the next video also. So once we have it, we add together. Adding x isn't that bad, 17x. Adding y's, hey, that's fantastic. That's exactly what we're looking for. When we have opposite terms and we add, opposites always add to 0, including opposite terms. Gone. On the right-hand side, be careful with your signs, please. I'm begging you, be careful with your signs. Negative 34 plus negative 1, said it. Negative 33 plus negative 1 is negative 34. If we divide by 17, which is generally our last step in solving for a variable with elimination method, all you have to do is add the system and divide. We're going to get x equals negative 2. Well, we got the first half. We have the x coordinate. Now, remember what I was saying a little while ago. Take that number, try it now if you can. Plug it into, not one of these, they're usually a little bit larger numbers. One of the original equations over here, I'd plug in, it doesn't really matter. I'd probably plug into this one. So let's try that. If you're asking why are you choosing that one? I don't know, it looked better. It has a smaller number to multiply by for your x's, and it has one less minus sign. That's the only reason. But it doesn't really matter. As long as you pick one of them and don't make sign errors, you'll be fine. So we plugged in -2 for x. We multiply, okay, that's -4. We got plus 3y equals -1. Let's add that 4. And if we divide by 3, we complete the other half, the y coordinate of our point of intersection. So that's supposed to be the point where those two lines cross. I don't care about this. Don't plug in your answer here. I don't care. I care about plugging into your original, because that's the two lines you're originally given. You need to find out where they cross. Let's make sure that we found that. -2 for x and +1 for y. You're going to notice I spent a lot of time checking for work. Why go through all this work to get an answer if you're not sure it's right? So take the time. Make sure that this is the correct answer before you go on, especially if you're doing like homework or a test or something. Why guess at it? Just take the 10 seconds it takes and plug it in. So that's -10 minus 1, well, that's -11. You can do it in your head if you want to. That works, it's great. This is -4, that's +3, that's -1. I know now, just by checking it quickly, that that is the point of intersection of that system of linear equations. That's the idea. Now we're going to move on a little bit more. If you want to pause the video, I need you to be very good at this, at least at the checking, at the understanding what to do from here. That's got to be there. That should be in the last video. Now we're going to progress a little bit onto, well, what happens if it's not so simple? Maybe this is not simple, but not like just multiplying one number. What if I don't have that option? How can we do that? So that's what the next two examples do. What I'd like to do is give you one that will work together and see if you can do one on your own. I'd love you if you pause the video after the next example and see if you can do the second one. I'll give you one more in just a moment. Let's work through this together. I'm going to start modeling my thinking for you. Just how I approach the problem, what I look for, what I'm thinking of while I'm doing it. Hopefully that'll help you to kind of build those thoughts into your head. Because what I really want to do, I'd love to brainwash you to think exactly how I think. That's a scary thought. But about math problems, so that you can look at it and ask yourself the same questions I'm literally asking you right now. So the first thing I ask is, what am I dealing with? Like, what am I even supposed to do here? Well, I'm looking at it, and it's going to say solve right above this. And so I'm noticing I've got two equations, each have two variables. That's a system of linear equations. I'm supposed to solve it. I know there's three ways to solve it. Number one way is graphing. I hardly ever do that unless I'm absolutely just asked for it. Number two would be substitution. Now let's see if that's a good option. Now it is an option, and it will always work, but it's not always a great option. Here's why. So I'm looking at this going, what would it take for me to solve for one of these variables? Because that's how substitution works. That's a lot of work. I don't want to do a lot of work. So I look down here. What would it take to solve for one of these variables? About the same amount of work. So I don't like that. So I'm looking at this again. You know what? Man, that's set up pretty well for elimination method in that I have all my variables on one side, my constants are on the other side, and my variables are lined up. That's looking pretty solid for me. So I'm looking at the problem. I'm identifying system of linear equations, I'm solving. Graphing, almost never. Substitution, no, because it's not solved for a variable. Elimination method, yes. But I'm thinking there's a problem here, because with elimination method, here's where some kind of novice students get stuck. They just start adding. like right now. They go, oh, let's add. Man, my variables are disappearing. Well, yeah, no kidding, because you don't have opposite terms. So I'm looking at this going, if I'm going to be doing elimination method, I must have opposite terms. I don't have them. So the next question that comes up in a lot of students' minds is, what's the right choice? The easy one. Technically, there is no right choice. So you can pick either term and make it opposite terms. That's fine. Either variable, make it opposite terms. But I would say, looking back over it, it's set up for elimination method. I need opposite terms. I don't have them. So I'm looking at the number I would have to make opposite terms. This would be a least common multiple of 12. This would be a least common multiple of 6. Do you see the 12 and 6? This, if you think denominators here, that would be, let's see, 4, 8, 12. This would be 3, 6. That's a smaller number. That's a smaller least common multiple. I'm going to make my y's opposite terms. That's how I do it. So I've looked at it. I've determined I'm using elimination method. I'm trying to find out which is the easiest thing to do, which is the easiest pair of terms to make opposite, and it's going to be the one with the smaller LCM, least common multiple. That's my y's. So I'm going to write up the number that I'm trying to get. I'm trying to get 6 here for my y's. Now, a good thing I'm noticing, so I'm looking at the problem, I'm also noticing I have opposite signs here. That's great. That means I don't need to multiply by a negative or anything. So I'm going to multiply to make my y's 6. Negative 6 on the top and positive 6y on the bottom. So let's multiply. Much like getting a common denominator, we're multiplying so as to change our terms into whatever number we just found out. So I've identified the elimination method, I'm working on my y's, I'm going to multiply this entire equation by 2, and this entire equation by 3. There was no way in this case to multiply one equation by one number and get these terms to be opposite terms. It's not going to happen. We need the whole LCM, lowest common multiple idea, to change both of them in this case. So let's multiply. Remember, probably the biggest mistake I correct on tests and homework and stuff is people will miss one of these terms by multiplying by that number. They almost never miss this because it's what you're trying to get. But they'll give me 4x minus 6y equals negative 13. They'll forget to multiply the other things. Please don't do that. So we're going to have 8x. We got a minus 6y. That looks pretty good. Equals negative 26. So we've just multiplied the top equation by 2. Now the bottom equation by 3. Why 3? Where's the 3 coming from? Remember, you've already determined that you're trying to make these terms have that number in front. Opposite signs are already there. So we're multiplying so as to create that number, very much like creating a common denominator. If we multiply every term by 3, we're going to have negative 9x. We'll have plus 6y. And we'll have equals 18. No, we won't. That can be 27. This is exactly what we want. Everything's still lined up. It looks fantastic, but look what multiplying did for us. Multiplying so as to create this term to be opposite actually did it. We now have negative 6y as a term, and we have positive 6y as a term. They're opposite terms. When we add them, and I mean the entire system, when we add this, we'll have, what's your sign? We'll have negative x. These are gone. If you want to cross them out, I love crossing stuff out. You just cross them out, and then you get positive 1. Is that good enough? Do you like that? Do you like negative x equals 1? If I say, hey, where's the point of intersection? Oh, well, the negative x coordinate is positive 1. That's so confusing. That's not an answer. I want what x is. So let's divide by negative 1 and get negative 1. So I know the x-coordinate of our point of intersection is negative 1. Do you remember where to plug in that negative 1? Do you want to use the stuff that you've made by multiplication, or do you want to use the original? Well, use the original, because what if you jack this thing up? If you made a mistake from here to here, it will not show up if you plug in the point to these two equations. So we're going to plug it into one of these. Which one and why? Because I'm trying to model my thinking. That one. I'd probably do that one. So even though I have a negative times a negative, I think positive, I'd have to deal with less negatives. That's why I'm doing it. So we plug in our x coordinate in this case. be careful on our signs. 3 times -1 is positive 3. If we subtract 3 and divide by 2, we complete our point of intersection. We get a y-coordinate of 3. Now let's make sure that we're right. So let's plug this into both of these. -4 minus 9. Let's see, -4 minus 9 is -13. Okay, that's, I know for a fact that that point is on that line. Let's see here. Positive 3 plus 6. 2 times 3 is 6. That's 9. So I know for a fact that that's the one point that's on both of those lines. If one point is on 2 different lines, it is the point of intersection. That's awesome. So now we know that we're right. I really hope this is making sense to you. I hope that when I do the recap right now that you're like, yeah, I totally get that. So when we're looking at solving systems, we're looking for the point of intersection. There are 3 ways to do it. Graphing is almost never a good choice for us by hand. The second way would be substitution. It's a great choice if you have one of the equations that solve for a variable or easy to solve for a variable. That's not here. So number 3, the elimination method works if we have everything lined up, x's, y's, and constants, and you have opposite terms for one variable. If you have that, you just straight up add the system, you're almost done. If not, you need to find the LCM, least common multiple, for one of those pairs of terms. Usually, you're going to pick the LCM, the terms that have the smaller LCM. In this case, that's the y's here. So we could have made the x's 12 and -12. We chose to make the y's -6 and +6. That's a smaller number, that's less multiplication. After that, then the same old thing. Add your system, divide, and then plug it into one of your original equations to find the missing half of your point. I'm going to put one more on the board. I would highly encourage you to try this on your own if you haven't done this one. Try it on your own. Start working through it. Let's see what we know about that one. If you had to think in your head right now, think it at me if you can. Think about the system of linear equations and tell me what you would want to do with it. Would you want to do substitution or would you want to do elimination? And think why. Why would you want to do one of those 2 techniques? Well, I'll tell you what, I don't want to do substitution. That looks pretty nasty. I don't want to start solving for a variable. It takes too much time and then we still have to go through the whole process of substitution. I like the fact that all my variables are on one side, they're already lined up, and I also like the fact that they have opposite signs for each pair of terms. That's fantastic. What I don't like about it is that I don't have opposite terms themselves. So I have opposite signs, but not opposite terms. So this is fairly well set up for elimination method and not very well set up for substitution method. After that, I'm thinking, well, what pair of variables would be easier to get opposite terms? If I look at the y's, yeah, you know what, they got opposite signs, but the LCM, the least common multiple there is 40. I'd have to multiply this by 5 and this by 8 to get 40. That's a pretty large number. So I'm going to look over my x's. Opposite signs is great. If you don't have opposite signs, you'll have to multiply one equation by a negative. If you don't have opposite signs, you'll have to multiply one equation by a negative. Is it hard? No, but it does lead to a lot of sign errors, so you have to watch that. We deal with that in the next video, by the way. So if I wanted to make opposite terms here, 40, 6. Let's pick the 6. So why don't you multiply, if you haven't done it already, multiply by what you need to in order to make 6 on both of my terms for both of my x terms. In the first equation, that's 2. In the second equation, that's 3. I don't need to multiply by negatives because I already have opposite signs. So let's explore that for a second. What if you didn't? What if you didn't have opposite signs there? Would you do 40? You certainly could, but 6 is still smaller. So here's what you would choose. You'd choose to either multiply this first equation by -2 or this bottom equation by -3, but not both. Can you see why not both? I mean, it'd be kind of silly, right? You'd say, oh, let's change the sign here and change the sign here. Well, then you have the same sign still. That's silly. So you pick one or the other. It does not matter which one, but you'd force this to have opposite terms. So if you have the same, if you want to make two terms opposite terms, you're going to multiply, and you have the same sign, multiply it by the number it takes to get your LCM, but also make sure that you're going to have opposite signs by multiplying one of the equations by a negative number. So let's change that back. I did have -3. I'm going to keep +2 because that's -6. I'm going to keep +2 and +3 because that's +6. I get opposite terms there. So let's go through it. So I'm seeing a -6x. I'm seeing a -16y, and I'm seeing that is probably the most common mistake I see, by the way, is when people get the variables and go, oh yeah, it's -6 and -16, cool, and they'll give me 1. It's so easy to miss. It's just really easy to accidentally do that. So be careful. Make sure that you're double checking and hitting every single one of those terms, including the constant, by whatever number you're multiplying. That's also why we don't use this equation to check our answer at the end. Because what if you did make a mistake? It's not going to show up. It shows up only here. Let's multiply the next one by 3. So 3 times 2x, that's 6x. 3 times 5y, well, that's 15y. 3 times 0, that's 0. Don't accidentally put 3. It happens a lot. Now that looks really good. So I've multiplied by two numbers and given me my LCM out of the smallest pair. We already had opposite signs, create some opposite terms for us. If we add that system, 6x plus, well, -6x plus 6x is 0. That's exactly what we want to happen. -16y plus 15y, well, that's -y. 2 plus 0 is 2. Yeah, we got to divide by a negative, but we're close to done. So we've just managed to solve for the y coordinate of our point of intersection. All we've got to do now is plug that -2 into one of our originals. I'm going to use that one. No negatives up there, not even a constant to deal with, so I'm using that one. And we can find our x coordinate. So 2x looks good. 5 times -2, not a problem. If I continue to solve this, we get 2x. Let's just change it to -10. So plus -10 is -10. If we add 10 and divide by 2, x equals 5. Let's double check, make sure we're right. So if I plug in, let's see, 5 here, that's -15. -15 minus, that's -16. -15 minus -16. That's what that gives us. 5 times -3 is -15. 8 times -2 is -16, but you're subtracting it, that's 1. I know that's right. So I know that point is on that line. Now we try this point on this line. So let's see, 10 plus, oh wow, that's cool. So 10 plus -10. That's 0. So I now know that that point is the point of intersection and therefore the solution to the system of linear equations. That's the power of the elimination method. You don't have to solve for a variable. It eliminates one variable straight from the get-go as long as you can make opposite terms and add systems. It's very powerful. We'll explore the utility in it next time. We'll do some more difficult examples on this. We'll talk about fractions. I mean, if you remember from substitution, dealing with fractions and substitution methods sucks. It's not fun. I think I made a huge mistake on it and looked at it for like 5 minutes or something just because of a sign error, but then the fractions come back and they get you. So with elimination method, we can get rid of fractions, where in substitution, you really couldn't. So that's one of the big things. We'll explore that in the next video. I hope you're doing well. I hope that this stuff is making sense. I really do. I want you to be successful at this. So let's put in some study time. Let's make sure that we get this elimination method. I hope that you do, and I'll see you for the next video.